Afternoon. I'm spot on weather meteorologist Matthew Euler. Welcome to my latest video. Now, today's video is going to be on the stratospheric polar vortex and blocking. Here is the overview for today's video. I'm going to start off with a stratospheric polar vortex definition. Next, we'll move on to stratospheric polar vortex characteristics. Then we move into stratospheric polar vortex disruptions, the troposphere-stratosphere coupling, and then the stratospheric polar vortex and the blocking. And then finally, I'll conclude by showing the references, the research I did, and the references I used. So first things first, the stratospheric polar vortex, what's the definition of this? The stratospheric polar vortex, which is abbreviated by the letters SPV, and I'm going to use this SPV, these initials, throughout the video. So whenever you see SPV, think stratospheric polar vortex. This is a band of strong westerly winds associated with cyclonic circulation that exists generally between 10 and 30 miles above the North Pole every winter. These winds enclose a large pool of extremely cold air, and the stronger the winds are, the more the air inside the polar vortex itself is isolated. That cold air is isolated from warmer latitudes to the south. And also, the stronger the winds, the colder the air gets. In the bottom right, I'm showing you an example of this red L, which represents the stratospheric polar vortex. And now keep in mind, the stratosphere is the second layer of the atmosphere. So we live here on the Earth's surface in the troposphere, but if we were to go up to the second level of the atmosphere, it'd be called the stratosphere. So this polar vortex in the stratosphere is really, really high up. Again, 10 to 30 miles above the North Pole every winter. And this just shows you the bottom right-hand graphic. That red L represents that stratospheric polar vortex. The blue coloring indicating the colder temperatures. And this oranger coloring here, like central U.S. south, is indicative of mild or mid-latitude air. And then you have this white line with the blue arrows that represents your jet stream. Now let's talk about the characteristics of the stratospheric polar vortex. So when the SPV is strong, the polar jet stream tends to stay farther to the north, and it's going to exhibit a more zonal west to east flow. So when I say zonal, I'm talking about the jet stream primarily blowing west to east. Okay, so we have a strong SPV. That polar jet tends to stay further north and exhibits a more zonal west to east flow. And at the surface, a stronger SPV is associated with colder than normal air across the Arctic region and milder air across the mid-latitude regions. And this happened, as an example, the 2019-2020 had a very mild winter because we had a very, very strong stratospheric polar vortex. And the polar jet stream pretty much blew west to east, like this diagram here in the bottom right. When you get a stronger, stable polar vortex in the stratosphere, you generally have a polar jet stream that blows west to east, and all the coldest air is confined up over the North Pole and the Arctic region that winter. The bottom graphics here showing temperature anomalies. The one here on the left, where I have my little red laser pointer next to, these were the temperature anomalies from December of 2019, and the orange coloring indicates above normal or warmer than normal temperatures, and you can see a big chunk of the U.S. in December of 2019 featured above normal or milder than normal temperatures for that particular month. Over here on the right, I'm showing an example of January 2020, so the next month. So December 2019 and January 2020, and it just got milder in the Midwest, the Great Lakes, New England, all the way up and down the eastern seaboard in January of 2020. And again, that was due mainly in part, to the stronger stratospheric polar vortex. And again, the orientation of the jet stream more west to east or zonal. Now, when the stratospheric polar vortex, when the SPV is strong, additionally, the Arctic oscillation, the AO teleconnection is often positive. Now, on the other hand, when the SPV is weak, it can be knocked off or displaced off the North Pole. And an example of this would be the February 2021 time period where we had the deep Texas that Texas deep freeze. The SPV is weakened when the strong atmospheric waves within the troposphere, that layer of air where our weather occurs, where you get these strong atmospheric waves kind of move from the troposphere and break upward into the stratosphere. And then as a result, the SPV, that stratospheric polar vortex, is going to slow. It may wobble. It may also split into several lobes, or the winds within the stratosphere may even shift from a westerly direction to an easterly direction. We'll talk more about stratospheric warmings here in a moment. So SPV disruptions cause a rapid increase in stratospheric temperatures, and that is called the sudden stratospheric warming. And I'm going to abbreviate sudden stratospheric warming with the letters SSW. Now look at this example where I have my red little laser pointer. The purple coloring in this example, bottom center, that indicates well below normal temperatures associated with that Texas deep freeze. This is February of 2021 temp anomalies across the U.S. And again, this purple coloring indicates double digits below normal temperatures from Montana extending all the way south to the Texas area, right? And then over here on the right, showing that a weakened stratospheric polar vortex generally results in a negative Arctic oscillation teleconnection. Here's a disrupted or weaker polar vortex. It shows that your polar jet stream becomes more wavier in its configuration. So you get deeper troughs, which allow Arctic air to spill southward into the mid-latitudes. And then you also get these highly amplified ridges, upper ridges, which allows warm air to move northward toward the Arctic. So the importance of the configuration of this polar jet stream, it becomes much more wavier or meridional, which means that now my upper level winds in the jet stream are blowing from north to south, or perhaps they're blowing from south to north, and less east to west, or west to east rather, zonal. Now, previous study links lower than average February sea ice extent across the Barents-Kara seas and a shift in the stratospheric polar vortex, SPV, toward Eurasia between the 1980s and the 2000s. This shift was accompanied by colder than average winters across Siberia and the middle latitudes of Eurasia. So, there are some studies out there that talk about, sea ice being lower than average, right? And that's associated with, some of these shifts in the stratospheric polar vortex. Bottom line is wherever the stratospheric polar vortex kind of goes towards, you're going to have the coldest, most bitterly air in the winter season in the northern hemisphere. In this case, is shifting towards Eurasia. Additionally, lower than normal sea ice over the Barents-Kara seas, along with a La Nina and an easterly quasi-biennial oscillation, or QBO, all favor a weaker stratospheric polar vortex during the winter season across the northern hemisphere. So this is something we'll keep an eye on here in coming winters. Will the sea ice be below normal over the Barents-Kara seas? Will we have a La Nina developed? Will we see this easterly QBO develop as well? That all favors a weaker stratospheric polar vortex. And when the vortex gets weaker, it tends to extend further south and displace off the pole. And it brings much colder, bitterly air into the middle latitudes. All right, so now let's move into the stratospheric polar vortex, the SPV disruptions. I'm showing on the diagram here on the left what happens. Let's start over here on the far left. So this is what these blue solid lines represent the polar vortex in the stratosphere. So initially, the polar vortex in the stratosphere is strong. The winds surrounding the vortex are more circular or symmetrical in shape. We have normal west to east winds in the stratosphere. They're above 60 degrees north latitude, up to about 19 miles above the ground. West to east winds is what you normally expect within the stratosphere over the pole. But what you get are these waves, represented by this solid arrow here. you get these tropospheric waves which go all the way up in the stratosphere and they begin breaking. It's called wave breaking. And what it does is over here on the far right now, you get just the right amount of these waves, these planetary waves to break in the stratosphere. It triggers upward wind reversals and warming of the stratosphere. So now these planetary waves break against the east to west roadblock, and actually the winds in the stratosphere reverse from a westerly direction to an easterly direction. We're showing you also, if you look at the peach color here, it's showing how the stratosphere, the polar vortex, is becoming more elongated or stretched out. Bottom left, we have a polar vortex reversal with the winds, warming spreading downward towards the Earth's surface, back towards the troposphere. The planetary waves break at the lower and lower altitudes within the stratosphere. And then finally here on the far right, the diagram is showing that sometimes reversal and warming will reach the top of the troposphere, where the planetary waves are confined to the troposphere where weather occurs. So bottom line is the shapes of this vortex do change over time. Now, I did spell it out over here on the right as well, saying that tropospheric blockings, or the blockings within the troposphere, are characterized by persistent high-pressure systems that can act as a source of planetary waves. These waves then propagate upwards into the stratosphere. That's what we're showing here in that far upper left graphic here. In a lot of cases, certain upper level blocking patterns tend to send those waves up from the troposphere to the stratosphere. It precedes those stratospheric polar vortex disruptions, in other words. And as these waves propagate through the stratosphere, they can deposit momentum, slowing down the westerly winds of that polar vortex within the stratosphere. And if the weakening is strong enough, it can lead to a sudden stratospheric warming event. Okay, so now let's move on to the stratospheric polar vortex SPV disruption types. We're going to talk about sudden stratospheric warmings, which can lead to displacement of the vortex, can lead to splitting of the vortex, and can lead to stretching of the vortex. We're going to talk about all of these now. All right, so for sudden stratospheric warmings, if you see the letters SSW, that I'm just abbreviating, sudden stratospheric warming, SSW, these are dramatic breakdowns of the climatological stratospheric polar vortex in the winter hemisphere. It was first observed in 1952 by Scherhag. These are sudden events. These sudden stratospheric warmings are sudden events in which this SPV breaks down in a few days, being associated with remarkable warming of the winter pole. Typically, you get tens of degrees Celsius at the 10 hectopascal level, which is 19 miles above the ground. Some incredible warming temperatures at that level of the atmosphere. And sometimes these temperatures can exceed 50 or 60 degrees Celsius of warming. Just incredible. Now, to be classified as a major sudden stratospheric warming event, the zonal mean zonal winds within the stratosphere, that 19 miles above the ground, at 60 degrees north latitude, they reverse or change direction from westerly to easterly. And that constitutes a major sudden stratospheric warming when these winds reverse from west to easterly direction in the stratosphere at 19 miles above the ground at about 60 degrees north latitude. Here's an example of a sudden stratospheric warming event. Look at the red colors and these darker colors within this kind of like reddish color. This indicates excessive warming in the stratosphere up over the polar area. Right here, I got my red cursor going. Okay, so this whole red area indicates stratospheric warming. We're looking at the 10 millibar level here, in the temperatures at the 10 millibar level. You'll notice that those temperatures are colder in the blue coloring here at the 10 millibar level, or 19 miles above the surface. You notice that here. But the stratospheric warming is concentrated over the Arctic. Now, this is an example of the evolution of the sudden stratospheric warming event in 2009. Now, 21 to 11 days before the sudden stratospheric warming, you have this dark solid line here with the arrows represent your stratospheric polar vortex. It's pretty circular in shape. It's over the North Pole. No big deal. We got these colder than normal temperatures, which are confined up to the Arctic area there over the North Pole, associated with this stronger stratospheric polar vortex. Now you get these waves, this wave energy to propagate into the stratosphere to really start breaking down the polar vortex and weakening it. And over here in the middle graphic, you notice how the solid dark line becomes more elongated or stretched. And you notice this orange coloring here associated with stratospheric warming. So we're starting to see sudden stratospheric warming taking place, and this is 0 to 10 days before the disruption. And then over here on the far right, you notice you have two lobes or vortices, 1 to 11 days after the event. You see you have a stretched out vortex lobe over here, and then one over on the North American side. So just kind of wanted to show you how the evolution looks like. Strong stratospheric polar vortex at first, 21 to 11 days before the disruption. Then 0 to 10 days before the disruption, you got major sudden stratospheric warming, and then more of a stretched out look to the stratospheric polar vortex. On the far right, you have two vortices. So this was a vortex split that occurred. Some of the indicators for sudden stratospheric warming events, ZD Lawrence, he has these available on the website out there over the internet. Whenever you see, so when you're looking at these tools here, indicators, we're looking at 10 hectopascals, so 19 miles above the ground at 60 degrees north latitude. We're looking at the zonal mean zonal wind here in the upper diagram. And notice over here on the y-axis, you go from negative 40 and all the way up to positive 50, positive 60, even above that. Now, this y-axis represents your zonal winds in meters per second. All right, and you notice you have a zero line here that goes horizontally across this solid white line. So, whenever these lines dip below the zero line in a negative territory, that is associated with a major sudden stratospheric warming event. This indicates, if you have positive values, that indicates westerly winds within the polar stratosphere. And then if these lines dip into the negative territory below the this horizontal zero line, that indicates a wind reversal from west to east. So westerly winds are associated with positive values for the zonal mean zonal winds, and negative values represent a change in direction to easterly in the stratosphere at the pole. And so this is associated with a major sudden stratospheric warming. It dips down to negative territory. Now, all these different color lines represent different weather models, but you kind of see what happened here. And this occurred between, looks like March 10th and March 15th in this particular year. Bottom here shows the 60 to 90 degrees north latitude average temperatures. And whenever you have a major sudden stratospheric warming, you're going to have these temperatures go up like this, more of a positive slope. And that indicates that we have warming temperatures with height with this kind of pattern. All right, warming temperatures within the stratosphere. So you notice on the y-axis over here, we go from 215 to 250 Kelvin on the y-axis for the temperature range. And you notice how these temperatures really warm here around March 5th all the way up to about March 11th. All right, additionally, sudden stratospheric warmings come into two forms, splits and displacements. During splits, the stratospheric polar vortex will split into two vortices of similar size at the time of warming. And during displacements, the stratospheric polar vortex is just simply going to shift off the pole. Now, in both of these cases, splits and displacements, the vortex, or if you have multiple vortices, are sheared apart, leading to irreversible mixing of potential vorticity and deceleration or decreasing strength of the polar vortex. One other thing I want to mention is splits are typically associated with more of a wave number 2 activity, while displacements are associated with wave number 1 activity. And I'll show you what wave number 2 versus wave number 1 looks like here in a moment. Intense wave number 2 results in significant changes in those zonal mean zonal winds within the stratosphere over the pole and planetary wave activity in the stratosphere. The development of sudden stratospheric warmings is often linked to enhanced propagation of planetary waves with the wave numbers 1 and 2 from the troposphere to the stratosphere. Additionally, White et al. In 2019 found that there is longer influence in the troposphere during the displacement events. whereas the split events exhibit an almost instantaneous response within the troposphere. And then finally, conditions are longer lasting after splits, with the focus of the coldest temperature anomalies across Eurasia. Not in all cases, but in many cases, when you have a stratospheric polar vortex split, the dominant vortex tends to usually set up over Eurasia. Again, it's not always the case, because we're dealing with the atmosphere here, and there's a bit of chaos involved in the atmosphere. So, it doesn't mean it's completely in gold that it's going to happen that way. But in many cases, when we have polar vortex splits, the dominant vortex kind of goes over to the Eurasia side. All right, so here are the examples of wave number 1 and wave number 2. All right, first of all, only waves of wave number 1 and wave number 2 are large enough to make it into the stratosphere. These are associated with longer wavelengths. All right, so when we talk about wave number, we're talking about long waves, all right, within the upper atmosphere. All right, so on the left here, I'm showing an example of what happens during wave number 1. With wave number 1 configuration, you get one long wave trough and one long wave ridge. So the gray colors indicate the troughing, the reds and maroon colors indicate the ridges. So you notice for the northern hemisphere circulation on this graphic on the left, we have, when I say wave number 1, we have one main trough and we have one main ridge across the northern hemisphere circulation, okay? That's what we're showing you here. All right, one main trough in the gray and the black, one main ridge in the maroon and kind of like the brighter colors here. All right, and what do we say about wave number 1? It generally results in a stratospheric polar vortex displacement. Now, what happens with wave number 2? We're going to get 2 long wave troughs and 2 long wave ridges across the northern hemisphere. And that is associated with the stratospheric polar vortex splits. So let's take a look at this. Let's try to see if we can identify here on this graphic on the right, the 2 troughs and the 2 ridges. Okay, so remember this maroonish color is the ridges. So there's one ridge here pressing up into, kind of extending north up into Alaska, the Bering Sea, the Beaufort Sea, up to the Arctic Ocean. We have one main huge upper ridge there. Then we have downstream of that ridge, what really looks like a blocking pattern there. Downstream from that is we have this deep trough across the southeastern Canada, extending down into parts of New England and the upper Midwest. Okay, so we got one ridge, one trough. Here's another ridge right here. See it right here? These are other ridges right here. We got high pressure over the Ural Mountains as well. And then we got another trough over the other side of the globe. So trough, ridge, trough, ridge. So we got a configuration of 2 troughs, 1, 2, and 2 ridges, 1, 2. And that is a wave number 2 configuration, or wave number 2 pattern. And only wave numbers 1 on the left, that kind of setup, and wave number 2 on the right are large enough for those waves to get up into the stratosphere. They're longer wavelengths, usually associated with blocking preceding sudden stratospheric warming events, and ultimately stratospheric polar vortex disruptions. All right, for stretching, stratospheric polar vortex stretching, this generally occurs when the SPV elongates, resembling a rubber band. The SPV stretching typically produces the coldest temperature anomalies across the eastern portion of North America, and its effects are more immediate when you get a stratospheric polar vortex stretching event. Generally, it's sending coldest temperatures across the eastern portion of North America, and its effects are more immediate and do not last as long as compared to a stratospheric polar vortex split. Now, Judah-Cohen et al. 2025, they just put out a research paper, in fact, a few weeks ago. They indicate in that research paper that stretching events are becoming more common during the winter season due to Arctic amplification, or this Arctic warming, where you're reducing the sea ice, right? The reduction in sea ice over the Barents-Kara seas generally results in the establishment of this blocking upper ridge over that Ural mountain area, the Urals area, and that is associated with a deeper Eastern Asian trough. And then you kind of set the whole northern hemisphere into, the wave configurations you need for a stratospheric polar vortex disruption. The wave number one, wave number two, right? Overwhelmingly, now this is a quote directly from Dr. Judah Cohen. He said, overwhelmingly, extreme cold and severe winter weather, heavy snowstorms, and deep snow are associated with these stretched events. So, just last winter, in the 24-25 winter, we had 10 stratospheric polar vortex stretched event. And it was really interesting to watch because when the vortex would stretch down into the mid latitudes, come off the pole, stretch down to the mid latitudes, it would get very, very cold. And then when it relaxed and contracted and the vortex moved back towards the North Pole temporarily, we'd have a little bit of a reprieve from the Arctic cold waves. So as the vortex kind of stretches and contracts and stretches and contracts, it definitely impacts the type of winter weather that you see down in the mid latitudes. You get these troughs that develop, and you get much colder air to come down into the mid latitudes within those troughs. And in a lot of cases, you got much colder than normal air. You get any kind of moisture overrunning it, you'll get more in the way of snowstorms. On the left here, I'm showing an example from Severe Weather Europe. This is an example on the left here of stratospheric polar vortex split. Blue colors indicate the actual location of the two vortices associated with this polar vortex split. And then right down the middle, you have just this anomalously warmer temperatures in the stratosphere over the North Pole. See that? Right at this location here, 10 millibar temperatures. So you got the split in the blue colors, two vortices, and then that very warm stratospheric temperatures between the two vortices. And then over here on the right, we have the stratospheric polar vortex stretching event. Notice how this blue color kind of represents the coldest temperatures. And so you see like this stretching event from up over the North Pole, just north of Greenland, through Greenland, southward, all the way into New England. Okay, and this is an example of a stretching event. Notice the configuration or the outline of this green color here. That is pretty much an elongated shape. Additionally, what happens after these polar vortex disruptions? Well, mean sea level pressure anomalies are over here on the left. So after a disruption, we're talking out to 30 days after, up to 30 days after the stratospheric polar vortex disruption. These are mean sea level pressure anomalies. The orange indicates above normal sea level pressure, so higher pressure is situated over the Arctic, and you get lower pressure beneath that into these mid-latitude areas from the eastern U.S. and eastern Canada through Europe and Eurasia. This is an example over here of the effects after a stratospheric polar vortex disruption. You're getting higher pressure over the Arctic, lower pressure in the mid-latitudes. Over here on the right, showing the snow anomalies. The same range here, out to 30 days after a stratospheric polar vortex disturbance. Now, these amounts are in millimeters. Here's your scale over here on the right. But in general, the green colors indicate above normal snowfall across the eastern U.S., above normal snowfall across a lot of the mid-latitudes there of Europe, and below normal snowfall up over the Arctic itself, because you're being dominated by warmer than normal temperatures and most likely a lot more ridging into the Arctic region in this case. Here is a great example of just the different types of disruptions, a nice summation of them. Over here on the left-hand column, we're talking about displacements, the middle center column, stretching events, and the far right column, stratospheric polar vortex splits. So we're given examples of each of these types of stratospheric polar vortex disruptions. So let's just start off here on the left with the displacements of the vortex. 14 to 17 January in 2005, we had a stratospheric polar vortex displacement where the polar vortex moved from the pole towards north of North America and West Greenland region. And the impacts on the displacement as that vortex moved off the pole, CAO is cold air outbreak in eastern U.S., and it really depends on the strength and duration of this anomaly. Now, over here in the center, let's look at examples of stretching events from the vortex. 11 to 20 February 2021, it happened. 20 to 28 December 22, it happened. We had warming of the polar stratosphere. It's usually focused in the North Pacific side. And then typically we get cold air outbreaks in Canada and U.S. east of the Rockies. And this happened I mean, this first one, 11 to 20 February 21, was associated with that Texas deep freeze I showed earlier. And then the 20 to 28 December 2022, that was that punch of just frigid air that basically just over spread the whole United States, specifically the East by Christmas Eve that year. And then over here on the far right, we got a stratospheric polar vortex splits, which occurred in February 2018 and January of 2019. They're often but not always associated with sudden stratospheric warmings. And then you have frequently North American cold waves occur with the splits, but sometimes with simultaneously cold waves in Eurasia. So sometimes you can get cold waves in both the North American side and Eurasian side associated with the two vortices of the polar vortex, but that's not always the case. All right, so now, hey, we can get these stratospheric polar vortex disruptions, but there's cases where you really don't have the coupling or the interaction between the stratosphere and the troposphere to really have any impact on the weather. So just because somebody says, hey, the stratospheric polar vortex is weakening, does not necessarily mean you're going to have impacts to your winter weather pattern. Okay, so that's what I'm showing here, that not every case of a weakened SPV is there a connection between the stratosphere back down to the troposphere. And there may be no significant changes to the winter weather at the surface. Over here on the diagram here on the left, there's not much in the way of coupling here in this example. You see that, when you see the words out of sync, that indicates there's no coupling between the stratosphere up above here and the troposphere here in the lower portion of the diagram. These are showing differences from average atmospheric thicknesses or geopotential height anomalies, with the purple and the grayish colors indicating below normal height anomalies, and then these peach colors indicating above normal thicknesses or height anomalies. Okay. Now, really, we'll determine if the purple or the salmon or pink colors extend from the stratosphere up here. Do they extend all the way down to the surface here at the bottom of the image? We only have one case in which this purple coloring kind of extends from the stratosphere down to the surface just after December 20th in this example, and that would be a case of where there's coupling. Whatever you see out of sync, we don't have the connection or the coupling or that energy transfer from the stratosphere back to the troposphere. Okay. Additionally, I'm going to show you an example now of strong coupling or strong connectability between the stratosphere and the troposphere. Now, why do I call it troposphere, stratosphere, troposphere? Because the wave energy that we talked about earlier, the planetary wave energy, it moves from the troposphere into the stratosphere to disturb or weaken the stratospheric polar vortex in the stratosphere. And then after that vortex is weakened, do we have some of that energy coming back to the troposphere or not? Now, this was an example showing this pink salmon color here. Does this reach all the way to the surface? Now, in this example here on the left, right where my red laser pointer is, this was an example between the 10th and the 20th of January in this particular year, where you have this pink salmon color go all the way from the upper stratosphere down to the surface. This is an example of a coupling effect. Okay, this is dynamic coupling between the stratosphere and the troposphere. Notice how these salmon colors again reach all the way to the surface right here between 10 and 20 January in this example. And this is called the paint drip effect. If you're watching paint dry, right, it's a tedious process. Same thing in the atmosphere. You're watching this energy kind of drip down towards the surface. These increased atmospheric thicknesses and heights descending to the lower stratosphere over a period of days to a couple of weeks. There's significant changes as a result of this coupling with the polar jet stream and the weather across the mid-latitudes in the winter season. Numerous studies, by the way, have revealed that the Arctic stratospheric polar vortex exerts a significant influence on the dynamic coupling between the stratosphere and that troposphere area. And oh, by the way, only about 2/3 of observed major sudden stratospheric warmings have an apparent downward influence on the surface. The other 1/3 of the major warmings likely either were not strong enough disruptions to reach the lower stratosphere or had an effect but the troposphere was creating stronger anomalies in the opposite direction. So literally, this is a great example. Okay, you can get a weakened stratospheric polar vortex all day long, but without this coupling from the stratosphere back to the troposphere, back to the ground, it doesn't matter. This was a case of mainly where things were out of sync. So that means there was really no appreciable changes to the winter weather pattern. But this one was that case again, the dynamic coupling. You got to get the dynamic coupling. All right, now let's talk about stratospheric polar vortex and blocking. Now, usually following a sudden stratospheric warming, the polar jet stream is going to often develop the wavy shape with deep troughs and amplified ridges that can become nearly stationary for days. This generally leads to more extreme weather patterns, blocking patterns, more extreme stuck in place type weather during the winter season. Now, beneath high pressure ridges, you're going to get warm air which floods north into parts of the Arctic, often driving extreme ice melt. And then within the troughs, you get some cold polar and Arctic air to fill those low pressure troughs, bringing wintry weather further south than normal. And I'll tell you this, just this past winter, the Gulf Coast snowstorm comes to mind. The East Coast, the Southeast Coast snowstorm, all the way down the beaches, getting accumulating snow. That's a case of where we had a very deep trough in place, extremely below normal temperatures. And then we had moisture overrunning those very cold temperatures at the surface, resulting in unusual winter weather further south, points that aren't accustomed to it. Now, research does link the stratospheric polar vortex SPV disruptions to extreme cold air outbreaks in the middle latitudes of the United States or Eurasia a few weeks after the event. Baldwin and Dunkerton in 1999 in their research stated that anomalously weakened westerly flow in the stratosphere can actually propagate downward into the troposphere, potentially leading to reduced tropospheric westerly flow resembling that during blocking. So we're weakening, in the Baldwin and Dunkerton case in 99, we're basically weakening the westerly flow in the stratosphere, that second layer of the atmosphere, and then that weakening of the westerly flow extends further downward into the troposphere. And this sets up more of a weaker polar jet stream and a wavier type jet and reduced strength of the wind speeds within the jet. Additionally, tropical teleconnections, such as ENSO, the El Nino Southern Oscillation, the MJO, the Madden-Julian Oscillation, and this QBO, the Quasi-Biennial Oscillation, can alter Arctic conditions, which then impact the weather across the mid-latitudes, encouraging the development of blocking. So, we talk about Arctic mid-latitude connection, right, with the weather. When we talk about the stratospheric polar vortex and what it's doing each winter. But let's not forget about the tropical pattern drivers. What is the ENSO state for that particular winter? Is it an El Nino? Is it a La Nina? Is it neutral? What about the MJO phase? Do we have vigorous, more active MJO? And what phase is that in where we're having the strongest upward vertical motions within the Indian Ocean and the equatorial Pacific Ocean? And the quasi-biennial oscillation is just simply the winds in the stratosphere over the equator. Okay, and they alternate from east one winter to west the next winter, back to east the following winter, and so on. Now, Zhang and et al. 2024 discovered they did some model simulation in their research paper. They discovered that model simulation showed a weak stratospheric polar vortex could cause more blockings to be generated over the Greenland area and move more westward than usual, while a stronger stratospheric polar vortex can cause more blockings to be generated south of Greenland and across Western Europe. So very interesting, hey, what's the relationship between the stratospheric polar vortex and the blocking patterns and where they set up in the northern hemisphere during the winter season? So very interesting. A weak versus a strong stratospheric polar vortex. Different results from the model simulation of where that strongest blocking was located. And additionally, Zhang et al., the same study, indicated strong Ural ridging exhibited an enhanced East Asian trough the following week. So you get the initial Ural ridging to set up, that upper level ridge over the Urals area. And then a week later, you get this enhanced or deepened East Asian trough with much colder air. And then you get an enhanced Greenland ridge at the same time, eventually leading to a negative tropospheric annular mode anomaly. So this is the this would be your North Atlantic oscillation. This can persist for up to 1 month, by the way, is what they discovered. Zhang et al. 2024. Additionally, let's keep going. Meanwhile, I had done a dupe there, looks like. Yeah, I did. So I'm going to keep moving. All right, so meanwhile, a weak Ural ridge. So let's say the upper level ridge over the Ural area is weaker. This generally tends to exhibit surface cooling over northern Eurasia without notable tropospheric annular mode anomalies. Occurrence of a probability of strong Ural ridges is higher. Believe it or not, we're talking about ENSO here. The occurrence of strong Ural ridges is higher during La Nina winters as compared to El Nino winters. Barrio Pedro and Calvo in 2014, in their paper, discovered that European and Atlantic blocking tend to precede sudden stratospheric warming events during El Nino, whereas Eastern Pacific and Siberian blocking are the preferred precursors of sudden stratospheric warmings during La Nina winters. So here it is again, the difference in the ENSO phase and its impacts and its role on blocking patterns. Here's an example of stratospheric polar vortex and blocking. Now, this is courtesy of Colucci and Kelleher in 2015. They did a research paper, and they included this in their research paper. So what we're looking at here is the sudden stratospheric warming onset, all right, the date of that onset in this vertical column here. The next column, we're showing the actual onset date. And then over here, I'm sorry, no, this is the onset of the blocking pattern. So onset, just think of the beginning of it. This is the decaying portion of the block, when the decay happened in the blocking. This was the duration in days of the blocking in this vertical column. And these were the latitude and longitudes associated with each of these blocking patterns. So here's some examples here. We go back to 1981, December 4th. We have the beginning of the sudden stratospheric warming on December 4th, 81. And then the onset of the blocking occurred 4 days later. And it lasted about 5 days at about 62.5 degrees north and then further to the west. Keep going down here. Let's go more recent here. How about 2010? In 2010, February the 9th, we had a sudden stratospheric warming beginning. And literally a day later, we already had the onset of a blocking pattern, which then decayed 17 days later on the 27th of February. So just wanted to kind of show you what, some of these relationships are. You can look at the sudden stratospheric warming, when it started, and just how long after the sudden stratospheric warming did you start seeing the blocking setting up, blocking pattern, and then how long did that blocking pattern last? All right, here are my references I used. I'm wrapping things up now in the video. Quite a few references. Again, this takes extensive time and research to really dig into some of this stuff. I try to highlight some of the key points from these various papers. I encourage everybody to, go in there and just do a Google search on stratospheric polar vortex, blocking. You're going to get a bunch of these articles are going to pop up. You can just click on. Some are free to view, but others require a subscription, unfortunately. So I just try to look at the ones that you just kind of view for free, but just kind of showing you the different papers out there. Additionally, I looked at these papers, these research papers that are out there as well. And then additional references I utilized. And then I believe that's the last one. So a lot of references. It takes time to really put these slides together, these videos. It takes a lot of digging into these research papers here to determine really what some of the main points the researchers were getting after, and I try to include those in here. So you can kind of see what others have already discovered in relation to the stratospheric polar vortex strength and the blocking patterns, or this coupling between the troposphere to the stratosphere back to the troposphere, or lack thereof. And then what type of disruptions are out there, some of the effects after the disruptions, some of the examples of what they look like graphically. And then we talked about, waves of wave number 1 and 2 configuration are large enough to result in these disruptions of the stratospheric polar vortex. And that's all I got, everybody. I really hope you enjoyed this presentation. I'm going to go back to the beginning here. This was stratospheric polar vortex and blocking patterns. Um, it just seems lately in the winter seasons that we tend to at least get some sort of weakening of the stratospheric polar vortex just about every winter. Of course, the 2019-20 winter, we pretty much had a record strong stratospheric polar vortex, which resulted in very mild temperatures. In fact, I remember I was coming back into Virginia around just before New Year's on 2020, no, late 2019, and it was like 75 degrees in Virginia. Kid you not. And we just had that persistent positive Arctic oscillation, the very strong stratospheric polar vortex all winter long. It was just crazy. All right, that's all I got for now. Future videos, I plan to cover Alaskan winters. And then I also am going to go back and look at some of the winter weather, the cycles of cold versus warm winters. I'm curious to see if there's any kind of pattern between, stretches of cold winters versus warm winters. So I'm going to do that. And I also may eventually delve down later in another video, talk about, you know, pressure patterns and how they could play into the following winter weather. That's all I got for now, everybody. I thank you for your attention and thank you for just taking the time to listen to the video. That's all I got for now, everybody, and take care and God bless everyone.